Hello, my name is Oleg and I'm excited to tell you about the first results of Ludyna Brain Project. But first I would like to explain the motivation behind it. AI that we use today is primarily mechanical and has its problems. The most notorious problem is that AI doesn't understand what it is doing, as seen in these images. In this video, AI doesn't understand what type of vehicle is in front of it. As you can see, AI does not learn in real time. Instead of learning this new type of vehicle while observing it, AI tries to match it with what it already knows. In, uh, in this video, AI saves the vehicle from a frontal collision but accelerates backward at full speed and hits the garage. It shows that AI has no idea what it is doing, and if it gets in a non-standard situation, AI behavior can be unpredictable and dangerous. As shown in this meme, at this moment we primarily use AI tech that is based on if-else statements about pattern recognition. Unfortunately, while helpful, this type of AI has no fundamental understanding of the environment. As a result, it can malfunction if it gets into situations that creators have not predicted by if-else statements. We need better AI to progress as a civilization. We must make AI understand if we want to progress and go beyond if-else statements. So the next AI is AI that understands. It is the only way. The solution to if-else statements in AI is a black box AI. A black box AI is not a new idea. For example, father of deep learning, Alexei Ivakhnenko, was inspired by the cybernetic concept of the black box. The black box is an abstraction representing a class of concrete open systems that can be viewed solely in terms of its stimuli inputs and output reactions. Our brain is a black box. In short, black box AI means that the user, programmer or engineer set up sensors through which AI will receive information such as eyes or ears, actions that AI can do, goals that AI should aim for. Then the user puts AI in a virtual or natural environment to learn, receive feedback and achieve provided goals. Because black box AI cannot use task specific if-else statements to do work by definition, it uses memory, planning and predictions to learn how to achieve its goals. You can learn more about black box AI at ludyna.com. Why couldn't we create good black box AI? Probably because we couldn't create human-like memory. To understand means to be able to predict, and to predict means to use the memory of similar situations or knowledge. Black box AI should use human-like memory to learn in real time, extract and search patterns, restore data from memory, forget memories, abstract or compress data to ideas, etc. All this means that memory is a vital and essential part of black box AI and intelligence in general. The problem is that current deep learning algorithms are not a good fit for this task. I decided to create Ludyna Brain Project to make black box AI. Ludyna means human in Ukrainian. Ludyna Brain can be used as a black box AI or memory database. I'm currently working on the memory database part of it, which I call Ludyna Memory. It is time to show you how Ludyna Memory works. This demo runs in um, in a virtual machine on a regular desktop using a single thread and without hardware acceleration. This example uses Simeon dataset of handwritten samples. Simeon dataset consists of almost 1600 samples of handwritten numbers. Application randomly divides samples into two datasets, one for learning, which I call a train set, and one for testing, which I call a test set. We can display any sample using the command show with ID as a parameter. For example, if we want to display a random test sample for number 7, we can use the command show test set 7. If we want the memory to learn samples, we can use the command learn. Okay, memory learned 1493 samples. During learning, we associate sample data with its appropriate digit label. So the next time we put similar data into input, memory can recognize it. Now we can test if memory can recognize patterns. For that we can use the command match. If we want to test it on patterns that memory doesn't know yet, we can use a test set. Our test set contains 100 samples and memory recognized 96% of them. Here we can see which sample IDs memory recognized and which are not. For example, memory successfully recognized a sample of digit 5 with ID 103. Let us see what it looks like and try to match it again. As you can see here, we have match results, and memory shows you what it thinks about this pattern. Memory thinks it's number 5 with a similarity of 93%. The similarity is a percentage of how similar input is to data in memory. Now let us match some patterns that fail at recognition. For example, for digit 8, the sample with ID 1127 failed at recognition. Let's test it. As you can see, memory for some reason thinks it is digit 9, not 8. It is because memory makes a mechanical comparison and doesn't understand what it means to be digit 8. We will add understanding later when implementing black box functionality. So what will happen if we learn all samples from test set? Let's try it. Okay, memory learned 100 test samples too. Now let's us recheck the matching. As you can see, because we learned all samples from test set to pattern matching is 100% correct now. Ludyna memory can also restore how it sees specific digits. We can do it using the command restore. Memory sees digit 8 like this. and this is digit 5. We can also delete memories associated with specific labels using the command delete. Memory deleted all neurons and lists related to label 8. Now let's us try to restore number 8. Data doesn't exist anymore. Let's us try to match again. As you can see, memory is failing to recognize the number 8 now. Everything else should still work. And if we will try to match all samples from test set, we will get this. Accuracy now is 90%, not 100%, and it is because we deleted memories of data as it's associated with label 8. So all samples with data that is 8 fail recognition now. Everything I'm showing here happens in real time without neural network retraining. It is impossible to do this with classic deep learning algorithms. Let's get back to our results. Learning speed is fast. What you have seen was done without multi-threaded hardware acceleration or even proper optimization yet. Ludyna memory requires only one neural network signal wave to learn information and only one neural network signal wave to match information. More optimization and improvements are coming to this algorithm. Ludyna memory has properties that can change how we do AI. It has dynamic learning in real time without retraining of neural network. It has transparent memory. Imagine being able to tell what data caused AI to make one decision or another. You will be able to see AI thoughts, which again is not possible with classic deep learning algorithms. And of course, we can restore data from memory. Uh, Minor feature, but you can get a similarity number between input and what we have in the memory. Here is comparison table between classic deep learning and Ludyna memory. But is Ludyna memory deep learning as we know it? The answer is no. Ludyna memory is memory even though it can mechanically search for patterns. Is Ludyna memory an artificial neural network? Yes, it is. Conclusions. By magic manipulations of the structure of neural networks, classic deep learning lost some valuable features required to build black box AI, such as data transparency, real-time learning, and the ability to restore or forget data. Ludyna memory retains these features, allowing us to build fractal memory on top of it, which will lead to black box AI that can understand. Thank you for your time.